button. Okay, so welcome to lecture 12 of 124103 Biophysical Principles. Today we will be starting a new topic. It's called fluids. And I thought that we'd do something different today. So in the past, I sort of gave the lecture. We first learned the concepts and the topics that we needed to learn, and then we had the workshop after that. I thought that for this lecture on fluids, we'll sort of combine the two, the lecture and the workshop, so that I'll discuss the concepts first, and then just after discussing the concepts or the topic, we will look at the relevant workshop problem as sort of an example. So we are directly applying the concepts right away as we learn them. Yeah. All right. So so we've so far in this course, we've been talking about solid objects, right? We started by describing how the object moves, and then we talked about why the object moves, and that's because of force. And then we went on to say that if there's a force, then this object can also rotate, if the force will provide a torque on the object. And last time with elasticity, we learned that the force can also deform the object. If you pull or you push on the object can deform, and you have stress and strain. But throughout those topics, we've considered solid objects. So with fluids, we will consider the two other phases of matter. So we know matter exists in three common phases: solids, liquids, and gas. When we say fluid refers to both liquid and gas phases. It's sort of, you can think about liquid and gas as materials that are free to flow, right? So they're like fluid. Okay? They can freely flow. So when we say fluid, it's not confined to liquids only. It can also refer to gases. Yeah, and a defining characteristic for fluids is that you need a container to contain fluids, right? So you need containers to contain liquids and gas materials. And so instead of talking about mass to quantify the fluid, it's more useful to think in terms of mass per unit volume. Right. Before, when we were talking about the object and we're looking at the force exerted on the object, we considered the mass of the object, but that's because we were mostly talking about solids. But when we're talking about fluids, remember, you need a container to contain the fluid, and so you have this volume where the fluid is contained in. Right. And so instead of quantifying fluids in terms of mass, it's more useful to think in terms of mass per unit volume. Okay. And mass per unit volume is what is called density. Okay. So density is defined as mass per unit volume. Okay, we use the symbol rho. So this Greek symbol, it's not a P. You can think of it as a fancy P or a curly P, but we read this as rho. It's a Greek symbol, rho. Yeah, mass per unit volume is density. So density is essentially mass divided by the volume of the object. An example of density, which is very common, and we will encounter this a lot, so it will be useful to write this down in your formula sheet. If you're making a formula sheet for the exam, it will be useful to write down the density of water is 1,000 kilograms per cubic meter, which means that in 1 cubic meter of volume, the mass of water contained in that 1 cubic meter of volume is 1,000 kilograms. So from there, you can see that the unit for density is kilogram per meter cube. We can get that from the equation. Yeah. So the unit for mass is kilograms, and the base unit for volume, it's length times length times length. So that will give you meter multiplied 3 times, or that's meter cube. Right. So here's one example. So density, of course, will also be relevant for solids. So solids will also have densities, because we can also think of solids as mass per divided by the volume of the solids. But for our topic on fluids, we will mostly talk about densities of fluids, like the density of water being 1,000 kilograms per cubic meter. But here is a good example of where thinking about mass per unit volume is more relevant than thinking about mass itself. So say, for example, you have here two objects, a brass, a cubic brass, and a block of wood. So say here they have the same mass. So the balance, the weighing scale is balanced, showing that the brass and the wood have the same mass, and therefore they have the same weight, because weight is just mass times gravitational acceleration. But you can see that the wood has a greater volume compared to the brass, okay, because the wood is bigger compared to the brass, and so the wood has a much greater volume compared to the brass. So they have different masses, but they have the same masses but different volumes. If you place the brass and the wood in a tank filled with water, you can observe different things happening between them, right? So density, that's equal to mass divided by volume. Okay, that means that density is proportional to mass and inversely proportional to the volume. Well, the two objects have the same mass, so let's see what happens to the density. So inverse proportionality, right, means that if you have a small volume, then that gives you big density, and if you have a big volume, that results to a small density, right? So that's what inverse proportionality means. So because the block of wood has a greater volume compared to the smaller brass, cube of brass, that means the block of wood will have a smaller density. Okay. And it has a smaller density even compared to the density of water, and that's why the block of wood floated. Whereas for the cube of brass, the brass had a small volume, and therefore it had a big density. Its density is greater compared to the density of water, and so that's why it sunk to the bottom. We'll talk more about relative densities between the object and the water later on, but this illustrates, how thinking about density, mass per unit volume, is more useful than thinking about just the mass of the objects themselves. Yeah, because then the volume becomes important now. Okay. Right. So let's look at an example. Yeah. So here is the equation for density. So let's look at a numerical example of how we can manipulate the equation for density to find mass or volume. So here, say, for example, you have blood. Blood has a density of 1,060 kilograms per cubic meter. And cerebrospinal fluid has a different density, a smaller density of 1,007 kilograms per cubic meter. So the first question asks us to find how much volume does 50 grams of blood have? Okay, and then, so here we want to find the volume. And then the next question, how much mass does the same volume of cerebrospinal fluid have? So in the second question, we want to know the mass. right? I'll give you a few seconds to think about this a bit while I'll write the equation for density over here. Right, so how do we find the volume from, we're given the density, so it's blood, and we're given the density of blood is 1060 kilograms per cubic meter. So we know density is equal to mass divided by volume. We're given the mass and the density, we need to find the volume. So we rearrange this equation. Okay, yeah, we've seen this kind of rearranging before, but I'll just emphasize it again. So the volume is below. So if I flip the equation so that you have 1 over density equals volume over mass, then I can multiply both sides with mass. That cancels out mass on the right hand side of the equation because mass divided by mass is equal to 0. Therefore, I have the equation for volume of mass divided by the density. Okay. Right, let's just do all the rearranging now. So for example, we again start with density equals mass over volume. And for the second question, we want to know the mass. So we isolate mass by multiplying both sides with volume. Okay, so we know mass is tied up with the volume via this division. And to remove this division, you do the reverse of operation, which is multiplication. That's why we multiply the right side with volume, so that volume divided by volume is equal to 1. But we have to do the same thing on the left side. So therefore, mass is equal to density times the volume. So we have these two equations that we can solve, that we can use to solve for the volume and the mass. Okay, so we can use the first one, mass divided by the density, to find the volume. But take note, the mass is given in grams. Okay. So you have to convert grams to kilograms. Okay, this is where we have to be careful with our units now because we're using derived units. Especially when we go to pressure later on in this lecture. And so yeah, start thinking about base units, SI units. So you have to convert grams to kilograms. Our conversion factor, 1000 grams is equal to 1 kilogram. Okay, or if we divide both sides by 1000, 1 gram will give you 0.001 kilograms. Dividing both sides by 1000. Okay, so when we do the conversion, 50 grams will therefore be 50 times 1 gram, but 1 gram is 0.001 kilograms. So 50 grams will be equal to 0.050 kilograms. Right, so we have our conversion and we have our units, and then it's just direct substitution for the volume. So volume is the mass. Again, make sure your mass is in kilograms because your density is in kilograms per cubic meter. So consistent units will give you this volume, 4.72 times 10 to the minus 5 cubic meter. Okay, for the next question, how much mass? So we want to know the mass, so we use the second rearranged equation. But this time we need the density of the cerebrospinal fluid. Okay, so that will be the density of the cerebrospinal fluid multiplied by the same volume as the blood that we found earlier. So that will be 4.72 times 10 to the minus 5. And that will give you a mass of 0.0475 kilograms. All right. Okay, are we happy with the solutions for the density? I think the main thing here is manipulating the density equation. So yeah, so if you want to save time in the exam, the format will be very similar to the test. So you've seen it's multiple choice. So if you want to save time, then you can just put these rearranged equations in your formula sheet already. So you won't have to rearrange. Okay, so the other feature for fluids is pressure, because we said fluids need a container to confine them in. And so if you put a fluid inside a container, the fluid will exert force on the walls of the container. So you'll have force pushing on the walls of the container, but instead of looking at just the force, the individual forces exerted by the individual gas particles, for example, that are contained in a container, it's more useful to think of the force per unit area. Okay, so how much force do the gas particles exert over an area of the container? Okay, and the force per unit area is called pressure. Okay. So if you put that into an equation, pressure, okay, so we use the capital P for pressure. Okay. Right, so that's different from density. So density is the curly, it looks like the curly P, which is actually rho. For pressure, it's capital P. And if we just put the definition for pressure in an equation, it's force divided by area. And if we work out the units, the unit for force is Newton, and the unit for area is meter squared. So the unit for pressure is Newton divided by meter squared, which is the same as the unit for stress that we learned last time. And we know that has a special name called the Pascal. SI unit for, or the standard unit for pressure is Pascal. You will commonly use Pascal, but just note that Pascal is equal to Newton per meter squared. So you have to be careful with your units again. Your masses should be in kilograms. Your lengths should be in meters. Okay. So similarly, pressure is inversely proportional to the area and directly proportional to the force. So say for the same let me just sort this out. Yeah. So say for the same area, my pen. If you're looking at the same area, okay, then a small force will give you a small pressure, right? Because that's what direct proportionality means. And a big force will give you big pressure. If you're looking at the same, if you have two objects with the same unit area, then yeah, the pressure will vary depending on the amount of force exerted on it. But if you're looking at the same force, so you have a particular area and you're exerting the same amount of force, inverse proportionality means that if you have, you're exerting the same amount of force over a small unit area, that will give you a big pressure over that small unit area. And if you have a big area, then that results to small pressure if you're applying the same amount of force, right? So inverse and direct proportionality. So thinking about inverse and direct proportionality, which object would you rather poke your skin with? So you have here a finger poking the skin, okay? And you have a needle poking the skin, and we assume that the force exerted by the finger is the same as the force exerted by the needle. right? So same force, but different, the same force applied over different sizes of areas will give you different pressures, right? Okay, so we all know that if you just poke your skin with your finger, it probably will hurt momentarily, but then that goes away, as opposed to poking your skin with a needle with a very small tip, very small area. The pressure will be so large that it can penetrate through your skin. Okay, right? So the same amount of force applied over different areas gives you different pressures according to that equation, the inverse proportionality between pressure and area. All right. So the concept of pressure also applies to solids. So for this particular example here, numerical example, let's look at the inverse proportionality between force and area and pressure because it's easier to visualize. Okay. So here a student has a mass of 83 kilograms and his sneakers have a total surface area of 0.0290 meters squared. How much pressure does the student exert on the ground? All right, so the equation relating pressure, force, and area is here. Pressure is force per unit area. The area is given. The area of the sneakers is given. The question is, what is the force? So you have the student, say this is the foot of the student, and it's exerting, it has, the student has a mass of 83 kilograms and it's exerting a force on the surface area. The question is, what will be this force that you need to consider in calculating the pressure that the student exerts on the ground? Any idea about what that force should be? Yes, yeah. So yeah, so you have the student has a mass and there's a gravitational pull on the student that's downwards. So yes, you're right, the force is coming from the student's weight that's exerted over the area of the sneakers. And recall that the weight is equal to mass times gravitational acceleration. So the student's weight is distributed over the surface area of the sneakers. So then pressure is equal to the weight, mass times gravitational acceleration divided by the area of the sneakers. Student's mass is 83 kilograms times gravitational acceleration 9.8, and that's distributed over the surface area of the sneakers 0.0290, giving you a pressure of this number, 28,048 pascals. If you write that in terms of prefixes, if you move this 1 to 3 spaces, then you'll have 28 times 10 to the 3. Times 10 to the 3 is kilo. So this is the prefix kilo, or times 10 to the 3. Right? Okay, so for this particular example, we used a solid object to visualize. So it's easier to visualize how pressure is related to the force exerted over an area. Okay, but if we apply that to fluids, let's think about the Earth's atmosphere. So the Earth's atmosphere is actually exerting a force on the surface of the Earth because the atmosphere is made up of air molecules and you know, atoms have masses, so you sort of have this weight force exerted by air molecules on the surface of the earth. So yeah, so you have this atmosphere, the weight of the column of air above us exerts a pressure known as the atmospheric pressure, right? Okay, so the earth is surrounded by this atmosphere, and if you just consider this column of air, then this column of air will exert a force on the surface of the earth. And that's what we call atmospheric pressure. Okay, so if we look at how the atmospheric pressure changes, so say for example in outer space where there's no atmosphere, there are no air molecules exerting force, and so the pressure is zero. But then as you approach the surface of the earth, okay, then you'll have more and more air molecules above you that's exerting downward pressure, a downward force, and therefore the pressure starts to increase as you approach the surface of the earth. And at sea level, okay, at this level, at sea level, the weight of the air pressing down can sort of be measured. So if you look at the weight of air pressing down on an area of 1 square meter, that would be about 101.3 kilonewtons of force. Okay. So this with 1 squared meter, this is the area A, and 101.3 kilonewtons, this is the force F. Okay. Right. So at sea level, if you just take 1 square meter of area, then the force exerted by the air molecules over that 1 square meter of area is about 101.3 times 10 to the 3 or kilo newtons of force. Right. And therefore, we can calculate the pressure at sea level. That's what we call atmospheric pressure. You divide the force, 101.3 kilonewtons divided by 1 square meter. So the pressure will be 101.3 kilonewtons per square meter. Okay. Remember that the prefix kilo is times 10 to the 3. So you can also say that the atmospheric pressure is 101.3 times 10 to the 3 newtons per meter squared. Okay. And newtons per meter squared has a special name. It's the Pascal. Right. So this is very common. I think we will mostly use pascals to quote pressure. Right. So instead of using kilonewtons per meter squared, it's the same as kilopascals, or times 10 to the 3 newtons per meter squared is times 10 to the 3 pascals. Okay. Right. So atmospheric pressure, it's because of the force exerted by the air molecules above us. And so we have seen now several units of pressure. So let me just summarize them. The SI unit for pressure is Newton per meter squared, or pascals. Okay, but another common unit is the atmosphere. Okay, right, atmosphere. And 1 atmosphere, that's the atmospheric pressure that's exerted by the Earth's atmosphere is equal to 1 atmosphere. And so in pascals, we've seen that in the previous slide, it's 101.3 times 10 to the 3 pascals. So you have this conversion factor if you need to convert from atmospheres to the SI unit pascals. Right, and this here just summarizes the different atmospheric pressures in terms of the different units that we've seen so far: Newton per meter squared, pascals, and atmosphere. Okay. All right, so we've seen so here we've seen that the pressure increases as we go down and approach the surface of the earth. Okay, and if we say, if we use this point as the reference point and say that's say 0 height, That means that if we go deeper, right? If we go deeper, that means that the pressure increases. Okay? And so even if you go swimming, for example, and if you dive, so for example, a person swimming in the ocean, as this person goes deeper, he will feel more pressure as he goes deeper, because the pressure increases as we go deeper. You can sort of logically think about that, as you go deeper, then you'll have more water above you that's exerting a force downwards, and therefore as you go deeper, more water molecules is exerting force downwards, and therefore there's more pressure being exerted on you as well as you go deeper. Okay, yeah. And so the deeper you go, the more pressure you feel, and usually we feel the pressure in our ears, because that's the sensitive part of our body to pressure. But the key idea here is that the deeper you go, the higher the pressure gets. Okay? Yeah, and pressure increases with depth. Again, you can think about that as the deeper you go, the more weight is being exerted, the more force is being exerted on you, and pressure equals force over area. So the bigger the force, the bigger the pressure, the deeper you go. Okay. So therefore, the total pressure when you go swimming and you dive deeper, the total pressure will then include the pressure exerted by the Earth's atmosphere. Yeah. So that will be the pressure provided by the atmospheric pressure, plus whatever pressure is provided by the water at a certain depth as you go deeper down the ocean. Okay. If we put that in an equation, the pressure at the depth will therefore be equal to the atmospheric pressure plus the pressure provided by, the water above you when you're at a certain depth h. Okay. So let's dissect this equation for a bit. Okay. So P here, that is the total pressure, it's also called absolute pressure. If you do the Google search or you check the textbooks, they sometimes call this absolute pressure, but absolute pressure just means total pressure. It takes into account the pressure of the atmosphere. So P0 here, it's the pressure at the surface of the water, and that's because of the atmosphere pushing down at the surface of the water. And we've seen earlier the atmospheric pressure is 101.3 times 10 to the 3 pascals. So the atmospheric pressure is sort of fixed. It's constant. At the surface, at sea level, at the surface of the ocean or the water's surface, the atmospheric pressure is 101.3 times 10 to the 3 pascals. So that is P0. You can think of P0 as a constant number equal to this atmospheric pressure. And then you have here the pressure that takes into account how deep you are in the water, and we call this the gauge pressure. Rho times G times H is called the gauge pressure, and that's the pressure due to the weight of the fluid above. Okay? Weight of the fluid, in particular the water above you. Okay, so therefore rho will be the density of the fluid, and H is the depth in the fluid, right? So the total pressure or the absolute pressure is equal to the pressure exerted by the atmosphere plus the pressure exerted by the fluid above the certain height or depth h. Okay, right. So let's look at a numerical example to see how that equation can be applied. So at what depth in the water would you experience a pressure of 2 atmospheres? Okay, so say so say you go swimming, that's the surface of the water, and the person is swimming, say, at this depth. Okay, the question asks, what should be this depth so that the pressure here is 2 atmospheres? Yeah, so that's sort of the visualization of the question here. So the total pressure, or the absolute pressure, is 2 atmospheres at the position where this person is at. Okay, and we're being asked what should be the depth, or how deep the person is from the surface of the water for this person to feel 2 atmospheres of pressure. Right, so we know that the total pressure P is related to the atmospheric pressure, so that will be atmospheric pressure, okay, at the surface of the water. Okay, so that will be P0, atmospheric pressure P0. Okay. And the total pressure should also take into account how deep the person is, because then there's the weight of the water exerting force and therefore pressure on this person. So what do we know? Okay, we know the density of water is 1,000 kilograms per cubic meter, and gravitational acceleration is 9.8 meters per second squared. Why do we need these values? Then we need them for finding the gauge pressure. Okay. Right. So remember, this bit is the gauge pressure, and this bit here is the atmospheric pressure. Right, so we need the density of the water, the fluid, and the gravitational acceleration in order to find the gauge pressure. And then we're also given the total pressure. It's 2 atmospheres. Okay. Remember, atmosphere is not the standard unit, so you have to convert that to pascals. Okay, the conversion factor, yeah, 1 atmosphere is equal to 101.3 times 10 to the 3 pascals. Okay, that's what the conversion factor that we've seen a couple of slides back. So therefore, 2 atmospheres will be equal to 2 times 101.3 times 10 to the 3 pascals. So that will give you a total pressure of 202.6 times 10 to the 3. So this should be an exponent. So yeah, please correct that in the slides. So that will be a times 10 to the 3 exponent 3 pascals for the total pressure. All right. So so we know everything. We know that we know everything except for the height, which is what's being asked. Okay, P0, yeah, that's the atmospheric pressure. It's 101.3 times 10 to the 3 pascals. That's the pressure at the surface. So we rearrange this equation to isolate for H. So P is equal to P0 plus rho GH. Yeah, so I'll just, you can rearrange this using the building up and tearing down process, but I'll rearrange this by using the other method. So you know H is tied to P0 by this plus sign. So if we subtract both sides with P0, then we get rid of this P0 on the right, and we have P minus P0 on the left is equal to rho GH. Okay. Right, to isolate H, it's tied to rho and G via multiplication sign. So if I divide the right side with, divide that by rho times G, I also divide the left side with rho times G. Rho times G cancels out. And then you have H is equal to P minus P0 divided by rho times G for the rearranging of H. And we know everything. We know the total pressure converted to pascals minus the atmospheric pressure, which is a constant number. That's the pressure at the surface of the water, divided by the density of water times gravitational acceleration. That will give you a depth of about 10 meters. Right. Are we happy with this solution for finding the depth? Good. Okay. Right. Okay, so we've seen that's the numerical example showing us how the total pressure depends on depth. Conceptually, okay, conceptually, so the total pressure just depends on the depth because the atmospheric pressure P0 is constant. It's a constant number. So if the density is the same, okay, so for the same density for an open container, yep, so for an open container, the atmospheric pressure would be the same. It's P0, 101.3 kilopascals. The pressure will then be the same at any given depth. And it does not depend on the shape of the container. Because as you can see here for the gauge pressure, it just depends on the depth H. And it depends on the density of the liquid. So if it's the same liquid as shown in this figure here, so say, just think about this as water with different containers of different shapes. If it's the same fluid, if it's the same fluid that's occupying the containers, regardless of what the shape of the containers are, the pressure at the same depth will be the same. The pressure at the same depth will be the same because then the depth is the same for all containers. The density is the same because it's the same liquid. Atmospheric pressure is the same. It's the same atmospheric pressure at the surface of the containers. Okay. And so, yeah. So the pressure will just be different if the densities are different. So the pressure will be different at the same depth if the densities are different. So be careful in analyzing this equation here for the total pressure. Yeah, you have to consider the density as well as the depth of the liquid. So in the mastery test, which is, I think it's already open, but it's not due until the end of the break, I think. But there's in the mastery test number 4, there's one question there that gives you a scenario of 3 different cylinders, cylinder A, B, and C. Okay, cylinder A and cylinder B have the same height. So cylinders A and B, they have the same height of 20 centimeters of liquid, but it's different liquids. So tap water and seawater, of course, having different densities. Okay, so the same depth, 20 centimeters, but different densities. Okay, and then you have cylinder C, which has a different depth, 25 centimeters, and also different density. Okay, so be careful in answering such types of questions. Okay, you have to consider, and you're being asked to rank the pressure at the bottom of each cylinder. So essentially, you're being asked to rank the pressure at the same depth, all of them at the bottom at the same depth. Okay, be careful to consider both the densities and the heights of the liquid above. All right. Of course, yeah, I'll let you answer this in the master test, but this is just one example of the direct application of what we've just learned about total pressure depending on the depth. But also you have to be careful and consider the density when you're looking at gauge pressure. Cool. All right. So because pressure varies with depth, we can also use that concept. That concept is used to measure the pressure. Yeah. It says here, because pressure depends on depth, then the change in the height of a column of fluid can be used to measure the change in pressure. Okay. And so the change in pressure, delta P, right? So in this case, delta P is pressure difference, depends on the change in the height of the liquid in the column. And the barometer and the manometer here, shown here, the barometer and the manometer are two examples of devices that use this concept to measure the pressure. Okay, so because when the pressure changes, the height in the column of liquid should change. Okay, and so by measuring the change in the height, the barometer and manometer is able to measure the change in the pressure in the atmosphere for the barometer and the change in pressure of a liquid in the case of the manometer. Okay. So let's look more closely into how these two devices operate. Let's start with the barometer. Okay, so the mercury barometer, mercury is commonly used to measure the pressure using the barometer. The mercury barometer essentially consists of a tube. Okay, so you have here a tube that is placed upside down in a dish filled with mercury. So you have this dish filled with mercury. Okay. What happens is that, of course, atmosphere, okay, the atmospheric pressure will push down on the surface of the mercury in the dish, in this container here. And the atmospheric pressure is exerted throughout the surface of the mercury on the dish, and that causes some of the mercury to be pushed into the tube. Yeah, that's placed inverted. So the tube is placed inverted. That means the open side is inside the mercury container with mercury. And so when atmosphere pushes on the surface of the mercury, okay, some of the mercury in the container is also pushed into the column in the tube, and the mercury in the tube rises a certain height, delta H. Okay, right. So if the atmospheric pressure changes, okay, then the height of the mercury column in the tube will also change, okay, according to this equation here, right? So yeah, if the pressure changes, okay, then delta H also changes. And by measuring how much delta H is, the change in the height, the barometer is able to measure the change in the pressure of the atmosphere, pushing down on this mercury in the container. All right. So say For example, 1 atmosphere of pressure is pushing down on the mercury in the container. How high will the mercury in the column go? In other words, if you have 1 atmosphere of pressure pushing down on the mercury in the container, that will cause the mercury to push into the tube. We are being asked, how high will the mercury in the tube rise for 1 atmosphere of pressure being exerted at the surface of the mercury in the container. Okay. And the density of mercury is 13.6 kilograms per cubic meter. Okay. Right. So we know that the height will change as a result of the pressure difference. Okay, so you have 1 atmosphere of pressure in the atmosphere, and you have 0 pressure in the empty part of the tube. Okay, that's in vacuum, therefore there are no air molecules. Yeah, we can consider that the air molecules there is negligible, and so the pressure is 0. If we rearrange this equation because we want, so rearranging this equation because we want delta H, we divide both sides with rho G. So delta H will be equal to the pressure difference divided by density times gravitational acceleration. Right, so the change in height will be the pressure difference between the atmospheric pressure and the pressure in the vacuum divided by the density times gravitational acceleration. A atmospheric pressure, that's P0, that's always 101 times 10 to the 3. Okay. Yeah, so atmospheric pressure, it's really just a constant number, 101 times 10 to the 3 pascals. The pressure in the vacuum is close to 0 because we can think of this as negligible number of air molecules, and so the pressure is approximately 0. Okay, then divided by the density of the mercury column, because it's the mercury that rises in the tube, times gravitational acceleration G, that gives us a height of 760 millimeters, 0.76 meters, or if you move the decimal place 3 places to the right, that will give you the prefix milli, or times 10 to the 3, minus 3 times 10 to the minus 3 of a meter. Okay, so that's how high the mercury will rise if there is 1 atmosphere of pressure pushing on the mercury column. And that's why this is a common unit where pressure is measured with. It's called millimeters of mercury. So which means 1 atmosphere of pressure is equivalent to 760 millimeters of mercury. So we read this as millimeters of mercury. Hg, of course, is the chemical symbol for mercury. And this conversion factor arose from our calculation, which means that if there is 1 atmosphere of pressure pushing down on the surface of this mercury container, then the mercury in the tube will rise by a height of 760 millimeters. Okay. It's quite strange to measure pressure in terms of height, right? In terms of the height of the mercury in this column, in this tube. But yeah, but it's because 1 atmosphere of pressure causes a rise of 760 millimeters in the height of the mercury in this tube, and that's why it's sort of used as a unit for measuring pressure as well. Yeah, and the conversion factor between them is this: 1 atmosphere is equal to 760 millimeters of mercury in the tube. Okay. Okay, so let's go now to the first question in the worksheet, which is concerned with different units of pressure. So we've now seen different units of pressure, pascals or newtons per meter squared, and then you have atmospheres, and then we've just seen millimeters of mercury as also a valid unit for measuring pressure. So the first question in the worksheet asks us, given these different units for pressure, determine the conversion factors for converting pressure measurements in atmosphere and millimeters of mercury into the SI units of pascals. Okay. So I'll give you a few minutes. Yep. So as I've mentioned earlier, we're combining the lecture with the workshop. So I'll give you a few minutes to sort of think about this problem and maybe attempt answering this problem, and then we'll look at the solution to this problem. So maybe about a few minutes, 2 or 3 minutes, and then I'll discuss the solution. And while you're doing that, I'll just pause the recording. Okay, so maybe let's look at the solution for this. So atmosphere, the conversion factor, we sort of, it's from definition. We've seen that 1 atmosphere is equal to 101.3 times 10 to the 3 pascals. So that's from definition. But if we wanted to find the conversion factor between pascals to atmosphere, meaning 1 pascals is equal to how many atmospheres, we can divide both sides by 101.3 times 10 to the 3. So that it's 1 atmosphere divided by 101.3 times 10 to the 3 gives us the appropriate conversion factor between 1 pascals and atmosphere. Right? And then 1 atmosphere is equal to 760 millimeters of mercury. We've seen that as the definition from the barometer example. Okay, and if we again divide both sides by 760, okay, right, then the right hand side will be equal to just 1 millimeter of mercury, and the left hand side will be 1 divided by 760, and we get the conversion factor between 1 millimeter mercury and the corresponding atmosphere unit. Okay, but we want to find 1 millimeter mercury. How much is that in the SI unit pascals? So starting from 1 millimeter mercury is equal to 1 atmosphere divided by 760 here. Or you can also start from here. 1 millimeter of mercury is equal to 1.32 times 10 to the minus 3 atmospheres. And then you use the conversion from atmosphere to pascals, which we've seen here. The definition. So 1 atmosphere is equal to 101.3 times 10 to the 3 pascals. And so 1 millimeter mercury is equal to 133.3 pascals. Okay. And so, this just summarizes all the conversion factors, which you'll probably find useful to put in your formula sheets. So given atmosphere to pascals, pascals to atmosphere, atmosphere to millimeter of mercury to atmospheres, and millimeter of mercury to pascals. All right. Okay, so those are the conversion factors. Typically, we will mostly use pascals. As I've said, the SI unit is pascals, but I think in some problems we'll also give it in terms of atmosphere. So atmosphere and pascals would be the common ones that we need to convert between. All right. So the other kind of instrument or device that measures pressure is the manometer. So the manometer measures gauge pressure. The barometer measures the atmospheric pressure. So it compares, the pressure at the surface of the mercury to the pressure in the column, right? But for the manometer, it measures the gauge pressure. So the way the manometer works is that you have it's like you have a tube. One end of the tube is open, so that at the open end you have the atmospheric pressure P0. Okay, we know P0 101.3 times 10 to the 3 pascals. Okay, and then at the other end is closed, and so the other end measures the pressure that we want to find out. For example, pressure of the blood, okay, blood pressure. And depending on, yes, so it compares the pressures between these two ends. And similar to the barometer, the difference in the pressure gives rise to the difference in the height of the liquids inside the tube. Right. So inside the tube, you have this liquid. Okay. And if the pressures at the open end and the closed end are different, then the height of the liquid at the closed end will also be different to the height of the liquid on the open end. So you have this difference in height between the liquid at the open end and the liquid at the closed end. Okay. And right, the difference in the height in the liquids is related to the difference in the pressure between the atmospheric pressure and the pressure that you want to determine. And so by measuring the difference in the height, you're able to determine what is the pressure that you're wanting to find at this closed end. Okay. Right. So the sphygmomanometer, the one that's used to measure blood pressure, is a specific example of that device that compares the height of the liquid inside the device to the pressure at the open end and the pressure at the closed end that we want to measure. Yeah, and so that's why if you notice, the doctor puts the closed end of the sphygmomanometer, at the same level as the heart, because if you want to measure the pressure, the blood pressure at the heart, so how hard the heart is pumping, and that measures the blood pressure, then the pressure at the same height is the same, right? So we've learned that the pressure at the same depth is the same, and that's why you put this at the same level as the heart. And and by measuring the difference in the height of the liquids inside the sphygmomanometer, the doctor is able to determine the pressure at the closed end of the manometer, which is the pressure, the blood pressure, as the heart pumps. Okay, in terms of blood pressure, there are two kinds of pressures, the diastolic pressure and the systolic pressure. The main difference between the two is that the diastolic pressure is just the minimum or the lowest pressure in the artery. And the systolic pressure is sort of, you can think of it as the maximum pressure. That's when the heart is beating. So when we say diastolic pressure, for example, the next problem asks us to find the diastolic pressure. When you read the word diastolic pressure, it just asks you to find the gauge pressure, meaning rho times G times delta H, the lowest gauge pressure. Is what diastolic pressure is all about. But to find the diastolic pressure, it's still density of the liquid or the fluid times gravitational acceleration times the difference in the height between where you are measuring the pressure from. Okay, right? So this is an example of finding the gauge, the diastolic pressure, which is also the gauge pressure. So remember, diastolic pressure is also the gauge pressure. Okay. So this question in the workshop, question number 2 in the workshop, Kate tells us, asks us to estimate the diastolic pressure for an adult giraffe. And an adult giraffe, a male adult giraffe, can be about 5.5 meters tall. So that will be from the head to the foot. That's about 5.5 meters tall. Okay, and the Hart's giraffe must be very powerful to pump blood to its head. And estimate the diastolic pressure for an adult giraffe. Okay. So we will so the giraffe's heart is in its rib cage, okay, somewhere around here. So that's the giraffe's heart. Okay, and we want to know how powerful, we want to know the pressure, diastolic pressure for the giraffe to pump blood from the heart to its head, from its heart to its head. Okay, we can approximate the heart to be, approximately midway. Right, so we can approximate the distance between the heart and the head to be half of the height of the giraffe. Yeah. So we can approximate the difference in height to be 2.75 meters, half the height. So the difference in height over which the giraffe needs to pump blood from the heart to the head. Okay, and we want to find the pressure for that pumping mechanism. It's not explicitly given in the problem, but the density of blood will be needed because it's the blood. The blood is the fluid that's being pumped over this 2.75 meter height. Okay. Density of blood is 1060 kilograms per cubic meter, which we've seen in the earlier slides. Okay, and which is probably one of the important constants that you'd want to put in your formula sheet if you're building a formula sheet. Right, so gauge pressure, we sort of already have a clue as to what equation to use because, the height, delta H, and then the density is also needed. So gauge pressure is that one that has rho times G times delta H or H. Okay. Right, G of course is 9.8 meters per second squared, and so we can find there the gauge pressure is equal to rho, the density of the blood, times G 9.8 times the height over which the giraffe needs to pump the blood to and from. So it's 2.75 meters. That's 28.6 kilopascals. Okay. Yeah, if you want to convert that to millimeters of mercury, then you can use one of our conversion factors and you can get that in millimeters mercury. But pascals, so 28.6 times 10 to the 3 pascals should be sufficient. Yeah, so the next question is just something conceptual. So for a giraffe to drink, it has to lower its head to the ground. What effect this has on the blood flow, and how the negative effects can be counteracted. Right, of course, when the giraffe bends over, the blood will drop from the head. The head will drop by about 5 meters going down towards the ground. And so you'll have the drastic change in pressure there. And in humans, that would cause some unconsciousness. But for giraffe, its body has mechanisms to counteract the sudden change in pressure when the head changes height, essentially goes from 5 meters to 0 meters when the giraffe bends down. And these statements here sort of gives you the mechanisms that helps the giraffe function without becoming unconscious. Yeah, and the next question is also conceptual. So the blood vessels in the giraffe's legs also have high pressure, because imagine, yeah, the blood pressure in the legs will support the full weight of the giraffe. And so you have a lot of force being exerted on the legs, and therefore you have a high pressure on the legs of the giraffe. And the giraffe is able to cope with this high pressure because it has tight skin, like compression stockings. Yeah, and so you can just read this statement to explain how the giraffe is able to cope with the high pressure on its legs due to the high force exerted by the weight of the giraffe. Okay. Right. Are we good with this problem, and can we move on to the next concept? Yeah. Good. Right. So the next concept is buoyancy, and buoyancy is also related to changes to how pressure changes with depth. Okay. So we've seen that the deeper you go, when you go swimming, the deeper you go underwater, the higher the pressure gets. Okay. And that makes it hard to submerge objects because of the pressure difference between. So here you have low pressure on the surface, and the deeper you go, the pressure increases. Okay. And because of the increase in pressure, it makes it difficult for objects to be submerged. And the concept, the specific concept related to the difference in pressures to the depth in water is called buoyancy. So let's talk about buoyancy. What is buoyancy? So consider this object that's immersed in liquid, let's just say it's water for simplicity. So we know we've already learned that okay, you have a lower pressure above the object, and the deeper you go, the pressure increases. So below the object, the pressure will be higher. And we know pressure is equal to force divided by area. Therefore, if we draw the force arrows, okay, you have a smaller force above the object compared to a bigger force below the object, okay, because the pressure is bigger below, and pressure is directly proportional to the force. So bigger pressure means bigger force. Smaller pressure above means smaller force. Okay. Right? So if we look at the net force along the vertical, you have a smaller force that's downwards, a bigger force that's upwards. What's the direction of the net force in this case? It will be upwards, right? Because smaller downward force is counteracted by a bigger upward force. You have this net force that is directed upwards. Okay. So you can think of this as the net force that is directed upwards. And this upward net force supports the object. It sort of provides the support to the object. And this upward net force is what we call the buoyancy force. So the buoyancy force is that kind of support force provided by the liquid surrounding the object, and it causes the object to be suspended in the liquid. Okay, so instead of calling it a normal force, because normal force is when you have a solid surface supporting an object. In this case, it's now the liquid surrounding the object that's supporting the object. And in that case, it has a special name. We call it buoyancy. Okay, of course, the object will also have a weight force. Okay, so any object that has mass will have a weight force, and weight force is always directed downwards. If the object is at rest, okay, if it's not moving, we say that the object is floating, and in that case, the buoyancy force is equal to the weight force. So it's really very similar. The function of the buoyancy force is very similar to the function of the normal force that we've seen, except that for the normal force, you have an actual solid surface that's supporting the object. For the buoyancy force, it's a fluid that is supporting the object. And if the object is at rest, then that means that the buoyancy force that is always directed upwards, always directed upwards, vertically upwards, is equal to the weight force for the object to be at rest. Okay, so buoyancy force, yeah. According to Archimedes' principle, the buoyancy force will be equal to the weight of the fluid displaced by the objects. It's now different to solid objects, because we know if you put an object in water, the object has volume, and so that object will displace some of the water in the container. Okay, and Archimedes' principle says that the buoyancy force is equal to the weight of the fluid displaced by the object. And it's this relationship that allows us to sort of calculate how much the buoyancy force is. Okay, yeah, buoyancy force is equal to the weight. So buoyancy force is equal to the weight of the fluid. Okay. Weight is equal to mass of the fluid times the gravitational acceleration, which is constant. Yeah, right. And then if you recall the definition for density, density is equal to mass per unit volume. And we rearranged this equation earlier. And we've seen that mass is equal to density times the volume. So if we rewrite mass of the fluid in terms of density, then buoyancy is equal to the density of the fluid times the volume of the fluid times G. Okay, so this is just going, yeah, we started from Archimedes' principle, which says buoyancy force is equal to the weight of the fluid that's displaced. Weight is equal to mass times gravitational acceleration. So that will be the mass of the fluid that's displaced. And then we use the definition for mass and density. Okay, so the mass of the fluid displaced is equal to the density of the fluid times the volume of the fluid displaced. And so therefore buoyancy force is equal to the density of the fluid where the object is immersed times the volume of the fluid that's displaced times the gravitational acceleration. And that's what this equation is all about. So just remember that in this equation, density refers to the density of the fluid, and volume refers to the density of the fluid displaced. It's not the density of the object in the fluid, and it's not the volume of the object that's in the fluid. It's actually the density and the volume of the fluid. Okay. The only exception is when the object is fully submerged, because when the object is fully submerged, then the volume of the fluid displaced is equal to the volume of the submerged object. Okay. Right, and I would say this is one very important concept, and we'll see some applications of this later on. But just, yeah, keep it at the back of your mind that when the object is fully submerged, then the volume of the fluid it displaces is equal to the volume of the object itself. Okay, so looking at some conceptual examples of Archimedes' principle. So imagine you're holding two bricks underwater. So say that's a container of water, and you're holding brick A here, and brick B is being held at a deeper, at a lower depth. Okay, so the force required to hold the brick B in place. So of course, brick A will experience buoyancy force, and brick B will also experience a buoyancy force. Okay, and the buoyancy force will tend to cause the bricks to float upwards if the buoyancy force is greater than the weight of the bricks. So you want to hold the bricks downwards with a force to counteract the buoyancy force. So that's the applied force. So the question is asking, if the two bricks are at a different depth, how do you compare the force required to hold brick A and brick B in place? Any ideas? What do you think is the answer here? This is a little bit of this is a little tricky. Yeah, the answer would be the same, because notice the buoyancy force only depends on the density of the fluid and the volume of the fluid displaced. So if the bricks are similar, so they have the similar shape and size, so that they have the same volume, then they will displace the same volume, and therefore they have the same buoyancy force. In which case you should exert the same amount of force to keep them in place. The reason why they will have the same buoyancy force, even if they have different depths, is going back again to the concept of pressure. So the pressure increases with depth, right? And pressure is equal to force over area. So let's consider this block here. So here on top of the block, you have low pressure, and below the block, you have high pressure. Okay, and say the block has a certain length. So this is the difference in the depth. Okay, pressure is equal to force over area. So this is the force. Okay, so this is, say, a lower force on top, and a higher force below, because pressure is directly proportional to the force. So say, for example, the pressure difference, let's say that's 1 Pascal, just for argument's sake. Let's just put a number. Yeah, because the difference in pressure between the top and bottom of the block, let's say, is 1 Pascal. There's a pressure difference because there's a difference in depth. Yeah, but then the deeper you go, the top part of your block will also be at a higher pressure compared to the top part of the block here. But also the lower part of the block will also experience a higher pressure. So the pressure on top will increase. The pressure below will also increase by the same amount, because you're keeping the same height. Like the depth increased by the same amount. So the difference in pressure here would still be the same, would still be 1 Pascal. Okay. And even if you go deeper, okay, you're still looking at the pressure difference between the top of the block and the bottom of the block. So the pressure difference will still be the same, even if you go deeper. I mean, we are comparing the pressure between the top part and the bottom parts of the block. Okay, so even if the block is here at the shallower part compared to the deeper part, the pressure difference will still be the same. Okay, because we are comparing the pressure between the top and bottom parts of the block. And therefore the force will be the same between the top part and the bottom part of the block. And the buoyancy force will therefore be the same regardless of whether you're at the shallow part or at the deep part. Does that sort of make sense? Yeah. Yep. So the buoyancy force doesn't depend on depth. The pressure depends on depth, but the buoyancy force depends on depth. Now, in terms of floating and sinking, so if the object is less dense than the liquid, it will float. I think this is from intuition, or at some point you encountered this, that if the object is less dense than the liquid, it will float. And if the object is more dense than the liquid, then it will sink. If we compare the forces, okay, right? So if you look at the free body diagram of this object, you have the weight force that's downwards, and you have the buoyancy force provided by the liquid, and the buoyancy force is always upwards. Okay, so let's consider the first case. If the buoyancy force is greater than the weight force, meaning, right, you have your free body diagram looks like this. Yeah, buoyancy force is greater than the weight force, then the net force will be upwards, right? Because your buoyancy force will be greater. So in this case, the object will tend to go upwards, and that's where we say the object will float. Okay. And looking at this free body diagram, then we say that if the weight, so this is the first case, if the weight of the object is less than the buoyancy force, then the object will float. Right? Okay. So it's equivalent to saying if the object is less dense than the liquid, the object will float. In terms of forces, if the weight force of the object is less than the buoyancy force, the object will float. And we've seen that from this free body diagram here. Okay. For the second case, if the buoyancy force is less than the weight force, so that the free body diagram looks like this, right? So the buoyancy force, the upward force is smaller than the downward force, then the net force will be downwards. And that will be the second case for when the object will sink, because the net force will pull the object downwards, right? So if weight of the object is greater than the buoyancy force, then the object will sink. Right. Okay, so sometimes it's useful to compare the densities of the object and the liquid to determine whether it will float or sink. But often, you're given the mass of the object, and so it's easy to find the weight of the object. And so by comparing the weight of the object and the buoyancy force, you can determine whether the object will float or sink. Okay, so we can look at this example as an application. A scuba diver, so this is question number 4 in the worksheet. So the scuba diver and her gear has a total mass of 72 kilograms. And together, the diver and the gear displace a volume of 69 liters. We want to find the buoyancy force on the diver when they're in seawater, and the density of seawater is given here. And then from there, after finding the buoyancy force, we want to determine whether the diver will float or sink. Okay, yeah, so we start with what we're given. We're given the mass of the diver and the gear combined. So we can just think of them as a single thing, single object. We're given the density of the seawater, and we're given the volume of the fluid displaced by the diver and its gear, which is 69 liters. So we know liters is not an SI unit for volume. The standard or SI unit for volume is cubic meters. So you have to convert liters to cubic meter. And the conversion factor between liters to cubic meters is this one. 1 liter is equal to 10 to the minus 3 cubic meters. Okay. All right. So have a think of how you can solve for the buoyancy force given, given what we know or what the problem gives us, and the conversion factor from liter to cubic meter. Yeah, the equation from Archimedes' principle, the equation buoyancy is equal to density times G times the volume of the fluid displaced. Okay, so this is the equation from Archimedes' principle. Buoyancy force is equal to rho times G times V. Okay, just remember it's rho, we're talking about the fluid, not the diver and its gear when we're looking at this equation for buoyancy force. So it's the density of the fluid times the volume of the fluid displaced. Of course, G is just a constant number. Right, doing the conversion first, 69 liters. You can write that as 69 times 1 liter. And 1 liter is 10 to the minus 3. So 69 liters is essentially 69 times 10 to the minus 3 cubic meter. Okay. And so buoyancy force will be the density of the fluid, in which case that's the seawater, 1030 kilograms per meter cube, times G, 9.8 meters per second, times the volume of the fluid displaced by the diver and its gear. 69 times 10 to the minus 3 cubic meters gives you a buoyancy force of 696 newtons. Okay, so essentially you have the diver, you have the buoyancy force that's always upwards, 696 newtons. The next question asks, does the diver float or sink? Do you think the diver will float or will the diver sink? Okay, what other force do I need to draw in my free body diagram? So this is the free body diagram of the diver. Is there a missing force in this free body diagram? Yeah. So the diver is being supported by the buoyancy force from the liquid. Okay. And of course, the diver has a mass. So yeah, correct. That's right, Nikita. So the diver would also have a weight force that's always downwards, right? The question of whether the diver will float or sink depends on the relationship between the buoyancy force and the weight force. Yeah. Okay. Yes. Yeah, I think, yeah, Oksana, you're right. The diver will sink. The weight force will be bigger. So let's prove that. Let's calculate for the weight force. So the weight force, buoyancy force is calculated to be 696. Was that 696? Yeah, 696 newtons from before. The weight force is simply mass of the diver and its gear times gravitational acceleration. Mass of 72 times 9.8 gives you 705.6 or 706 newtons. Yeah, so that means the correct free body diagram should give you a longer weight force compared to the buoyancy force. Right, so that the net force will be downwards, and that downward net force will pull the diver downwards, and the diver will sink. Right. Good. Are we happy with this question and the solution and the analysis? Right. Okay. So the next question is also about buoyancy, and it's an old problem to check. Yeah, it's a conceptual question, but you can also solve it by using equations. But you are in a rowboat on a small lake, and with you in a rowboat you have a large granite rock. The density of the granite rock is 3,300 kilograms per cubic meter. If you throw the rock overboard, what will happen to the level of the lake? Does it rise, fall, or stay the same? So say you are riding on a boat on a lake, right? So excuse my stick figure drawings. Okay, you're on a boat, you're holding a heavy granite rock, you're on a lake, and then you throw the stone, the rock overboard. Okay, what do you think will happen to the level of the lake? Will it rise, meaning okay, will your boat sink? I mean, go down so big because the level of the lake rose, or will the level stay the same? Okay. Same as before, or do you think the water level will fall so that your boat will sort of move upwards? Okay. So from an observer on the shore, for example, looking at you and your boat. Okay. So there's a guess there, water will rise. Okay, any other guesses? Okay. Should rise. Okay, we will see. Let's look at this. I guess the best thing is to observe this what happens, right? So there's this video here. So let me know if you can hear the sound. So can you hear the sound? Is the sound? No. Okay. So let me fix that for a moment. Maybe I need to share. Okay, let's try this again. Can you hear the sound?
So can you hear the
Hello,
sound?
Can I ask you a scientific question? I've got a boat, right? Imagine it's floating in a pool, and there's a rock in it. Now, what would happen if I throw the
Okay,
rock
good.
overboard into the pool? Would the water level in the pool go up or down? Or do you reckon it'd stay the same? I reckon it'd stay the same.
I would say it would go up.
Stay the same. You want me to show you? Yeah, come over here. Robert Oppenheimer, famous physicist, very smart. He got this completely wrong as well, according to legend. So did I. So it's very difficult. All right. Well, here's a swimming pool, a bit rough. Here's a boat, and that's your rock. Put the whole lot in. So there we go. Water level, mark it there. Happy? All right. Here we go. Rock goes overboard. Boat goes in. Where's the water level? Have a look. Which is weird, right? Yeah. It's gone down. What happens is an object that's floating displaces a volume of water that has the same weight as the object, but an object that sinks, that only displaces its own volume, not its weight worth of water. And so when the boat goes back in, the water level stays down. So there you go.
Yeah.
There you go. Thanks very much. We've all learned something. Yeah, that's really good. Yeah. Thanks for letting us know. Cheers, mate. No worries. Thank you. Nice to meet you. Have a good day.
Yeah, that was tricky. That's really a tricky question. As he said, Robert Oppenheimer, famous physicist, also got that wrong. So intuitively, yeah, it defines it is unexpected, but I guess the proof is in the pudding, right? So we observed it clearly. The water fell when the rock was thrown overboard. And as he explained, the difference there is that if you have an object that's floating, the object will only displace the fluid. The object will displace a fluid that's the same as its weight. Whereas if you submerge the object, then the object will displace a fluid the same as its volume. So floating object will displace a fluid equal to its weight, and a submerged object will displace a fluid equal to its volume. Right. So if you work that out, so here is the submerged rock. So submerged rock will displace the same volume of water as its volume. So the water displaced, the volume of water displaced will be equal to the volume of the rock. But for a floating object here, the rock displaces the volume of water equal to its weight. So you have mass of the object divided by the density of the fluid. Mass is equal to density times the volume of the rock. Okay, and that's divided by the density of the fluid. So I express the mass in terms of density times volume because what the problem gives us is the density of the rock. So we're given the density of the rock is 3,300 kilograms per meter cube, and the density of water is 1,000 kilograms per meter cube. So if we divide those two, density of rock divided by density of water, that's 3,300 divided by 1,000 is 3.3. So the water volume of the water displaced is 3.3 times the volume of the rock. So here is a numerical proof that if the rock is floating, then the volume of the water displaced is 3 times the volume of the rock. Whereas if the rock is submerged, the volume of the water it displaces is just equal to the volume of the rock. So less water is displaced by the submerged rock. It's just equal to the volume of the rock. So the lake will fall when the rock is thrown overboard, which is totally unexpected. All right. Yeah. Any question about the lecture? Because then that ends our lecture on fluids. We learn about density and pressure, and then gauge pressures whenever you get the pressure relative to the height or the depth of where your object is located at. So whenever you read in the question, solve for the gauge pressure, then you need to consider the height or the depth of where the object is at, and the density of the fluid where the object is immersed. And total and absolute pressure considers the atmospheric pressure and the effect of the depth on the total pressure. Archimedes' principle is a consequence of pressure changing with depth. You have density of the fluid displaced times G times the volume of the fluid displaced. All right, any questions at all, or is there anything else you want us to talk about? So then we've now used both the lecture and the workshop time to talk about the lecture concepts, and we've looked at some problems from the workshop as well. No questions? No questions on the lecture? Okay, so in the worksheet, there is one question that's sort of, yes, yeah, you will need time to digest the topic. And yeah, I realize it's quite heavy. So actually the topic starting now with fluids, and then next time we'll again talk about fluids. They're sort of quite heavy topics, and it will need time to digest. So I will let you do that. In the worksheets, there is one question that's related to last week's topic on elasticity. I don't know if you want us to go over this question. I realize the topic is heavy, topic on fluid is heavy, and we've been going on for almost 2 hours. So we can, if it depends on what you want to do, we can look at the solution of this. Otherwise, I can put up a recording working through the solutions on stream, and you can look at that on your own time during the break. Yeah, so what do you want to do? You want us to look at this, the solutions of this stress and strain question? Yeah, I would think recording would be good. I think we've been going on for quite some time, and the brain is probably saturated with topics on fluids, pressure, buoyancy, and all of that. So yeah, so I think that's a good plan. Okay, I'll put up a recording in the same folder for the Albany resources, walking through the solutions for this. It's just because we didn't get the chance to look at an example problem last time on elasticity. Okay, good. Then if there are no questions on fluids or any other questions, it's the break. Okay, this is the last lecture before the break. So enjoy your 2-week break. Have a rest so that you'll be ready, and take care and keep well. I will still be available here for the review workshop. I don't know how many will show up, or which topics people want to talk about during the review workshop. So if you want, you can go to the review workshop at 1, or I'll also run it online and in QB5 as well. But yeah, otherwise, if there are no questions, then I guess I'll wish you a good weekend, a good semester break, and I'll see you in 2 weeks. Will we go over the mid-semester test at any point? We can go over that during the review workshop. Yeah. So if you want to go over the mid-semester test, then I think, yeah, let's go over that during the workshop at 1. All right. So see you in a bit.